thanks for the introduction, Martin. And it's great to be back in Fairbanks. I spent, I think, about 8 years here total, and so it really feels like home. Good to be back here. So as Martin said, I've done a lot of work on looking at how icebergs calve into the ocean. And so I want to try to summarize some of the things that I'm working on, and which I think is a very different way of thinking about calving than people have traditionally thought about. So what we've done is we've gone from thinking of calving of icebergs as being something that's beautiful and fun to watch, as a tourist. So here's a nice video from Tim Bartholomew gave me from Yahtzee Glacier, and just showing icebergs calving in. It's a really, I think, a pretty majestic video. But I'd like you also to, as you watch these icebergs fall into the ocean, think about what's happening to the water here, the waves that are produced, the splashing that's occurring. There's so much activity, just even from these pretty small icebergs, there's a lot that's happening in the water there. And so what I'm going to talk about is why we've gone from thinking of calving as just being something that's fun to looking at to basically to this, to trying to describe that sort of behavior using equations and models. And so the story that I'm going to tell tonight has roots in several different places. I'm going to start by giving some background on what was known about calving and what the sort of the traditional perspective was, which a lot of that came from Alaska, particularly on work on Columbia Glacier, but also on a handful of other glaciers in the area. I'll also talk quite a bit about the field work that I've done with Martin and a number of other colleagues at Jakobshavn in West Greenland here. And then from there, I ended up moving to Chicago and ended up spending a year doing laboratory experiments on iceberg calving, which is a kind of unheard of in the world of glaciology. People studying glaciers usually get into it because they want to be out in the mountains climbing or skiing. That's sort of the initial attraction to the field. So it's sort of unheard of that somebody would spend a year or so in a big city doing experiments. But there's things we can learn from each of these places that tell us something about calving processes and why calving might be important. So in the traditional view of calving, it's sort of thought of in terms of an ice dynamic or glacier mass loss process. So if you look at a glacier that calves into the ocean, you can say the position of the terminus, so the end of the glacier, is basically a function of the flow of ice coming down to the ocean, and also a function of how fast you calve icebergs into the water. And I think this is exemplified really nicely from time-lapse imagery. Here's a video that was given to me from Shad O'Neill, who's now at the USGS, of Columbia Glacier. And basically what you're going to see is one image a day for several years, and you see the ice is flowing from right to left into the ocean, but at the same time, the terminus position is not changing all that much from one frame to the next. Because this spans close to, I think it's 7 years, maybe 6 years, the terminus is actually retreating back, and so they had to shift the camera from one year to the next. But I think this really nicely demonstrates the idea that the location of the terminus is a function both of ice flow and of iceberg calving. I'll just let that run to the end then. I think it's almost there. Okay. So for a glacier that's in what we would say in steady state, one that's not evolving very rapidly, these two components tend to be about the same order of magnitude, which means that the terminus isn't going to change very much. It turns out there's some pretty complicated feedbacks between what controls calving and what controls ice flow. I don't want to get into the details too much there, because that could be a whole other talk on its own. But I'll just suffice it to say that you can, once you start calving, if you increase the calving rate of a glacier, that can change the flow speed, which can then promote more calving and can lead to very rapid retreat. And this is especially important when looking at glaciers that have a bed which is below sea level and is also goes to lower and lower elevation as you move up the glacier. So if you walked up the glacier and you were able to look down at the bottom, you would see that the bottom is getting lower and lower. So in this sort of situation, you can get a very rapid retreat occurring once you initiate this retreat in some way. And a great example of this is, again, at Columbia Glacier. What happened here was prior to about 1980, the glacier terminus was right in this area. It was sitting on a shallow shoal of sediment. And then right around 1980, the glacier was thinning. It retreated off of that shoal into deeper water. So if I go back to this picture, in 1980, the glacier was sitting right here, right at that shallow point. It started to retreat back, and then it initiated a very rapid retreat. And so this is just showing the location of the terminus at different points in time over the last about, I guess, 30 years here. And it's continuing to retreat up into this branch here, and it's expected to continue retreating for quite a while. So then you might ask, how can you initiate an irreversible retreat, such as what we're seeing at Columbia? And I should say, by irreversible, what I mean is, once that glacier starts to retreat, it's very hard to stop it from retreating or to get it to re-advance. And that's related to the dynamic feedbacks between calving and ice flow. So one way that you can initiate an irreversible retreat is just to melt the surface of the glacier and make it thinner. That's one way you can do it. Another is to change the temperature of the ocean in some way or another. So sort of a typical picture that I have about how fjords work, and there's a lot of debate about whether this is, how correct this is, but you have a fjord that comes in, it discharges fresh water right here from the bottom of the glacier. It comes out, it mixes with relatively warm, salty water. By warm, I mean a few degrees above freezing, but compared to the ice and the fresh water coming out, that's actually pretty warm. It mixes, rises to the surface, and then flows out as a cool and relatively fresh plume of water. So if you were to, and by mixing here, what this does is it's bringing warm water into contact with the glacier where it can promote melting, which can then lead to this destabilization. So you could change this water temperature, bring more warm water into a fjord, maybe change the discharge here. These sorts of things will have an impact on how much melting happens at the terminus, which can also destabilize the glacier and cause it to start retreating. So this idea was based largely on work from Roman Motika that was done on LeConte Glacier in southeast Alaska. And so I think prior to about, let's just suffice to say, there was a lot of work done on tidewater glaciers sort of historically in Alaska. And so there's a lot of knowledge that's been gained here and has now been applied elsewhere to similar systems elsewhere. And that's actually what drew us to Greenland in the first place. As Martin was saying, we were working on Jakobshavn Isbrae. It's a fast-flowing glacier that drains the western part of the Greenland ice sheet, about 6% of the ice sheet. You can only see a little bit of the glacier right here. It's actually would be flowing down from the ice sheet, calves icebergs into this fjord. So this white is all sea ice and icebergs, and then this all moves down into Disco Bay. As I'll show in a second, this glacier has undergone a very large retreat, which is quite similar to what we've seen at glaciers in Alaska. And because people like Martin and other colleagues of mine have had experience working on these sorts of systems in Alaska, there was sort of a natural attraction for us to go to Greenland and think about the processes there. This is a really spectacular place. I was really happy to have an opportunity to spend some time there. In addition to doing field work, I managed to squeeze in a little vacation and got to know some of the people living there, do some dog sledding. This is a photo from town, so just spent some time around town. And then here's this would be a photo from the helicopter trip coming back from our camp. So the picture that we've seen in Greenland is okay, let me just give you some background. This is, Jakobshavn is right here. This is the west coast of Greenland. It's about 69 degrees north. This would be Disco Bay right in here. So what we've seen is that in the 90s, there was a pulse of warm water in the ocean that made its way up the coast of West Greenland into Disco Bay towards Jakobshavn. And this is data coming from fisheries, basically, that are monitoring it. They're trying to figure out, how are the different fish species doing and how is that related to water temperature. So if we just continue watching this, you'll see that in about 97, 98, suddenly this whole picture turns red. And that's just indicating that the water has become warmer in West Greenland. Just let it go one more time. So in the early 90s, it's mostly blue. This pulse of warm water makes its way up the coast and into Disco Bay. As that warm water got into the Disco Bay and the fjord of Jakobshavn, we saw some pretty dramatic changes happen on the glacier. This here is showing surface elevation measured from an airborne laser altimeter. So there's a plane, NASA plane, that flies over the glacier every year, measures the surface elevation. So these different curves are just indicating the surface elevation at different years. Black is 97, going down through this orangish color is 2003. And here on this, so if on the horizontal axis here, we're at the glacier terminus, and then we're moving up glacier. So you see the surface rises as you go up the ice sheet. And then what you see is right around 97, 98, the same time that warm water was entering the region, the glacier began to thin. And it thinned, this scale is, well, this is 200 meters down to sea level. So it's thinned by several hundred feet over a matter of a few years. At the same time that thinning was occurring, the glacier also started to accelerate. So here now we're looking at velocity profiles derived, I think, well, at least primarily from satellite data. And this is showing, this is the velocity at the glacier terminus. You move up glacier, and then the velocity starts to decrease. That's typically what you expect for a tidewater glacier. These curves down here are all from, well, 1985 or the early 1990s. There's a data gap right when things start getting interesting, which seems to always be the case. And then you get into the late 90s, 2000, early 2000s, and you see that the velocity of the glacier has doubled, which is a very dramatic change. And the other thing to point out, for a glacier, these are really high velocities. We're talking 10 kilometers a year, 6 miles per year at the terminus. That's very fast. So we had thinning, we had acceleration, and as it accelerated, the ice began to stretch, and large cracks opened up in the glacier, basically started to fall apart. So here are some Landsat satellite images from 2000 onward, and I'm just going to show you how the terminus and the lower reach of the glacier changed during basically the last 10 years. So this is where the terminus was from about I think over the last 50 years at least, it was a fairly stable position. The glacier fluctuated a little bit back and forth around this line, but not very far. So that's in 2000, right as the thinning and acceleration is starting. You see it's retreated a little bit by 2002. There's some large fractures and rifts that have formed. It just looks like it's tearing, it's about to fall apart. By 2003, we've already had a pretty large retreat. This is still the terminus from 2000, and so it's retreated quite a bit just in 3 years, and that retreat has continued. This is where it was in 2010, 10 miles or so back from where it was in 10 years prior. And in 2010, when I first put together the slide, that was the historical record. It's now back, I don't know, 1 or 2 kilometers from where it was at that point in time. So the retreat continues. And it's sort of hard to imagine that it would stop retreating anytime soon. Because we do know that the bottom of the glacier is well below sea level, and it continues to be well below sea level for quite a long ways up into the ice sheet. So our original motivation for going to Jakobshavn was primarily just to study the ice flow, to see how does the ice sheet respond to these changes that have occurred at the terminus. We got there, spent some time at our camp, and pretty quickly got distracted by these very impressive calving events that occurred. And like often happens in science, we just followed what we thought was interesting, or at least what I thought was interesting. So I started thinking about calving and thinking about the tremendous amount of energy that can be released as an iceberg falls into the ocean. And here's basically why. Here's an example of one iceberg that we saw in 2008, I believe. The dimensions here are they're pretty hard to fathom. This is 1 kilometer across, so half a mile, 200 meters, so 600 feet or so above sea level as this iceberg is capsizing. But most of the iceberg is actually below sea level. You can't see most of that iceberg. So try to put that in perspective to buildings that around town, or it's so huge. It's way bigger than any building on Earth, any man-made building. Or, well, buildings are always man-made, but bigger than any man-made thing, as far as I can figure. So we got distracted by these calving events, started making time-lapse images of them. So we had a camera running, taking photos every 5 seconds or every 10 seconds, just continuously hoping to capture some of these calving events. And here's the same event that I showed on the previous slide. Several of these big icebergs breaking off. And I'm just going to let this play a couple of times so you can try to grasp how much energy there is in this system. To give you a sense of scale, the distance from this side of the glacier across, that would be a few miles, I guess. So that would be sort of like standing at the university here and looking down at the airport. That sort of distance that we're talking about. And I'll let it play one. Just notice how everything was pretty quiet before the event started, and then suddenly the whole fjord becomes active. You can actually see, if you watch carefully, you can see waves propagating through this pack of icebergs, bouncing up and down. So this here is actually ocean with icebergs floating in it. You can't see the water. There's such a dense pack of icebergs there. And of course, it's good to have more than one observation of whatever process you're studying. So we made lots of these videos. Here's another event. This one is I think it's 5 seconds between photos. So this goes on again for about a half an hour. You see the whole fjord is active. Icebergs are slowly rolling over. Keep in mind this is sped up quite a bit too. So when these big icebergs break off, it takes about 5 minutes for it to roll over. So when you first see the event starting, it's not always clear. You're kind of standing there and wondering, is the iceberg breaking off? Is it rolling or not? Because it starts so slowly and things are so far away. And I'll just show one more. This is from 2008 as well. I don't know how well you can see this one, but same general idea. Just that we have lots of observations of these events now. You can see some of these. You can see. I don't know if it's snow or ice particles or water or what that's spraying up, but it's spraying up over the top of the terminus. So observing events like this one in Greenland at Jakobshavn, but also at other glaciers such as Columbia, where there's a lot of work going on, we've sort of been forced to think about calving a little bit differently. Instead of thinking of it just as something that's important for glacier dynamics and glacier mass loss, it's also a source of energy. And this energy can have all sorts of implications, can produce ocean waves that I mentioned. Well, it makes quite a bit of sound. I'll play a sound clip later. We can record that. We can use that sound as a form of information to think about calving or to record calving events. Seismic waves that can be detected far away, and also things like generating turbulence in the water, potentially promoting more calving by, as the iceberg falls over, it might hit the glacier and promote additional fracturing, and can also cause a breakup of fjord or ice coverage like sea ice and the dense pack of icebergs. So first I'll just talk about these different ways that we can record calving events. I think that's probably the utility of studying waves that are produced by calving events, is that we can record them from safe distances and hopefully use them to say something about changes in calving or the processes that are driving calving, or just a way to quantify, how big was the iceberg that broke off. You can't just go out there and measure the iceberg, but maybe if you can come up with some nice relationship between the size or shape of an ocean wave, then maybe you can say something about the iceberg that broke off. So here I'll play a sound clip that we recorded at Jakobshavn. I'm not going to play the whole thing because we'd be sitting here for an hour listening to it, but I'll let it go for a couple of minutes. I don't have it synchronized to a video, so just close your eyes and imagine watching that huge iceberg roll over in the first video, and just enjoy. these microphones were located pretty close to the camera, so they're, again, pretty far away from a lot of these sources of noise. And what we've started doing is using this sort of information, these sound clips, to compare it to other data that might be more abstract. So, for example, at the same time that we were recording these sound clips, we also had seismic data that we were collecting with seismometers. It's not always clear how to interpret seismic data. We don't know exactly what's making the ground shake. But if you can hear at the same time as you're looking at seismic data, that's just another way to sense what's going on. And we're not limited to recording sound above ground either. Aaron Pettit, who works here at UAF, has started collecting underwater sound with hydrophones and is doing the same sort of thing, but it's just a different way to collect data. So as I said, these calving events cause the ground to shake. They generate seismic signals, and the seismic signals tend to be pretty unique. I'm not going to go too much into the details, but just say here's an example of one from Colombia. Here's one from Jakobshavn. This is just the data recorded by a seismometer indicating how much the ground was shaking back and forth. And you can see, they have some sort of similar patterns, several peaks, gradual growth and decay. They last quite long. They look very different from tectonic earthquakes. So what this means is that if you place seismometers near a glacier, you have another way to record information about a calving event. Of course, you could just use cameras and sit there all the time, but that's time consuming. With cameras, you have problems with clouds or rain or we're at high latitude, so in the wintertime you can't get observations because it's dark. So seismometers are just yet another way to record information about calving. And I think that's sort of where we're going, is that there's no perfect instrument for recording calving, so we have to use a variety of instruments together. It turns out that these big events, such as the ones I was showing in the video, they can produce earthquakes that are detectable globally. This is just a figure I grabbed from a publication that was in Science a few years back, where they had used a global seismic network, seismometers located all around the planet, identified some unique seismic signals, and then located them and found out that those signals all originated from the termini of different glaciers in Greenland. So you don't even have to be sitting next to the glacier to have some understanding of what's happening. And then again, ocean waves are yet another way to record information about calving. Also, this is, all of these things I'm presenting are fairly new ideas, and we don't have a good understanding between, the waves that are produced and the calving events itself. So it's still very exploratory work, which I think makes it really fun. But it's also challenging because you end up getting into things that you don't know anything about. For example, my background is in glaciology, but suddenly I'm thinking about ocean waves and how does the ocean respond to some sort of forcing. That's not something I have very much training in, but just because I was sitting at the terminus of Jakobshavn and watching these events, I started to get curious about what was happening in the fjord and also in Disco Bay out here. And so I just want to show some examples of the ocean waves that are produced, I guess mostly just as an illustration of, again, how much energy is released by these calving events. So this is the fjord. It's all ice covered with icebergs and sea ice. Our camp was right here. This is where the photos were taken from for those videos. And we've operated tide gauges pretty close to our camp. We managed to find little pools where we could stick a pressure sensor in the water. We've also had a tide gauge out in the town of Ilulissat. And then these 3 dots are indicating locations of seismometers. Actually, we've also had a seismometer right at our camp as well. So here's just an example of a wave that's produced by a calving event. The top panel is, well, it says it's filtered, but don't really worry about whether or not it was filtered or not. This is just an indication of the wave that's produced. I've removed any tidal signal. That's another way to think of it. And so you see that there's a wave that comes in close to our camp, has an amplitude of a meter or a few feet, and you could see that in the time-lapse videos if you were looking carefully. You could see the icebergs bouncing up and down. But then what I think is also interesting is that after that, you see these slower oscillations. They're pretty small, but they continue on for quite a long time. And if we focus just on these oscillations right here, which is what I've done on the bottom panel, you can see that there are some waves with an amplitude of a few centimeters or an inch or so. It's not, the amplitude isn't very large, but what's interesting is that the oscillations continue on for hours. This is going half a day, these oscillations continued. It turns out you can actually observe those slow oscillations with seismometers. So I'm going to now look at some data from this seismometer right here, and basically what we see is that after some of the calving events, the ground is flexing. As the wave comes in and propagates towards the station Ozzy, it's the town of Oziat, this whole bay starts to rock back and forth, and the ground flexes. And so this is the seismic data from that station. The seismometer can record vertical motion, and it can record horizontal motion. So this top one is the vertical motion. This is the motion of the seismometer in the north-south direction, and this is the motion in the east-west direction. And I've just looking at the data in a couple of different ways. The black curve is indicative of a calving event, which we know from comparing photographs to seismic data. We know that this black signal is indicating that there was a calving event. And then shortly after the calving event, you look at this orange signal, and you have these slow oscillations that continue again for many hours. And so we feel pretty confident that these oscillations are due to these ocean waves, and we think that the waves are actually what we call seiches, or it's sort of like a wave that you could produce in a bathtub, where the whole bathtub sloshes back and forth. And so we think that the calving event causes this entire fjord to rock back and forth, and also can cause this bay out here to rock back and forth, and to record a signal that you can observe seismically. This is a distance from the town of Oziat to the terminus of the glacier. That's about 60 miles. This is not unique to Greenland, of course, and so I've got a video here from Chris Larson at UAF, which I think is a very nice demonstration of the waves that are produced. This is sped up by, I think, a factor of 100, maybe 50, I forget. But you see just how dynamic this fjord is. Besides seeing the icebergs coming in and out, you can see the waves that are oscillating back and forth. And this is the sort of thing that I don't think anybody really thought about, except for maybe tour boat captains, trying not to get hit by big waves on their boats. But the fact that these fjords are so dynamic, I don't know if anyone has thought of it quite this way before. And part of it is just that we weren't there to observe. We're continually getting better instruments. We're able to produce high-rate photos or videos and speed them up and just look at these systems a little differently than we have in the past. And then the other thing is that there has been a new interest, or a broader interest, in glacier-ocean interactions because of large changes that are happening in Greenland. So there's also more people going to these places and looking at what's happening. One of the problems with doing field work is that it's often difficult to observe certain things. For example, in a fjord, you don't want to be very close to an iceberg that falls in the water and rolls over, because you might not live to tell about it. So another way to look at this is to start doing lab experiments. Is just an example from one that we were doing in Chicago. We're using plastic blocks that have a density very similar to ice, so we're basically thinking of this as a small iceberg, and we let it roll over and watch what happens to the water. We can measure the waves that are produced by tracking a buoy. We can measure how much energy is released by this iceberg, how much energy goes into the water. Those are things that are really difficult to measure in the field, if not impossible. Okay, so far I've talked about measuring or recording waves that are produced by calving events as sort of a way to quantify events, or maybe to say something about the physics of calving. I just want to spend a few minutes now talking about some of the other implications of this energy release. In particular, I want to talk about the idea of turbulence that's being generated in the water. I'm not going to talk about these because I haven't spent much time actually thinking about that yet. Okay, so here's another experiment just to demonstrate the turbulence that's produced in the water. This is just uniform tap water. It's fresh water. No salt has been put in, and we're just going to watch this plastic iceberg capsize and put a little bit of dye in the water and watch what happens. So this is at laboratory scale. Imagine if this was also happening in the fjord and it happened once a week, or however often calving events happen to be occurring at a particular glacier. So this is just a demonstration. But what we can do is we can measure the energy that's released and figure out how much is put into the water. It turns out that a lot of the energy that's released by a calving iceberg actually does go into the water. And so what that means is that there's a potential to do a lot of mixing. We don't have a good way to quantify that yet. There's, the process of actually mixing different waters is pretty complicated, and it's a difficult thing to calculate. But what we can do is just do some back of the envelope calculations and say, if all of the energy that was released by an iceberg went into mixing the water, and there was no energy lost to anything else, to heat or to waves that would radiate away, just say everything goes into mixing, we can put an upper bound on how much impact a calving event can do. And so for a typical large event at Jakobshavn, you could actually mix a pretty large portion of the water under those assumptions. But again, this is an upper bound. It could be that the calving events really don't actually do that mixing. It's something we don't know, and I would be willing to accept that it's maybe not important. But if nobody asks the question, then we won't have the answer to that. If you are able to mix the water column, what happens to this picture of fjord circulation? Suddenly, this warm, salty water gets mixed with the cool and fresh water at the surface, and I don't know, does it become easier to circulate water or more difficult to circulate water? I'm not actually sure what would happen. It's a very open question at this point. And so as we move forward in trying to think about calving, I see sort of two things happening. One is that the lab experiments that I've been involved in are going to become more and more sophisticated and try to replicate what we see in the fjord, or in a fjord. So here's an example where we actually made a stratified water column. The dark blue is very salty water, and then the lighter color, clear at the top, is basically fresh water. And you can see that there's a nice eddy that forms. There's actually a wave that propagates at the interface between the fresh water and the salty water. This is sort of a first attempt at trying to understand mixing. In this case, the final water column doesn't look that much different than the initial water column, but we're dealing with very strong stratification here. This is much denser than the water usually is in a fjord, and this is much less dense than the water would be at the surface of the fjord. So it just becomes really difficult to mix those two water columns. But anyway, this is where I see our research in the lab going, and just trying to make more and more sophisticated measurements. And at the same time that that's going on, I see people doing experiments or measurements in the field in a way that they're sort of turning the field into a laboratory, doing things like, here's a video from Tim again, very nicely has synchronized video with, this is a clock that tells you the time very accurately. You can compare that to seismic data. And so as you watch this video go through, you can actually see when are different portions of the seismic data occurring with respect to when the iceberg falls in the water. And I think in this video you actually see there'll be a big splash that comes up as the iceberg falls in. That seems to correspond to this peak in seismic energy right here. I'll just play that one more time. So I sort of see the lab or the field experiments just becoming also more sophisticated, and also attempting to measure more things at the same time and having very good timing on things so that you can compare different data sets. There's the big splash, which corresponded to that peak in seismic energy. And so I think this is really, it's been a pretty exciting area to work in, just because it is such a new field, and it's very multidisciplinary too. So I end up spending time thinking about glaciology, but also oceanography, seismology, collaborating with people in very different fields than what I was originally trained. And so then we can ask, where are we at now? What have we learned so far? So I talked about this traditional viewpoint of calving, and that was that calving is important basically because it's going to affect affects calving mass loss. I meant to say glacier mass losses. So calving is important because it affects how quickly a glacier can lose mass, how much ice or fresh water is put into the ocean. And that viewpoint is still valid, and it's probably still the most important reason to study calving. But there's this emerging viewpoint, which is that calving is a quasi-periodic source of energy. And there's, as I've been saying, there's a lot of open and intriguing questions remain. So thinking about how can this energy be measured, and how can you use those measurements to understand calving in terms of, I guess especially in the context of glacier change. So if you can, somehow build an algorithm using, I don't know, seismic data, and use that to detect calving events, suddenly you can look at changes in calving rates over seasonal or annual timescales. And then there are these other questions that I think are really interesting, which are thinking about sort of the oceanographic consequences of calving. Are the waves that are produced, are they important? How do they affect interpretation of data? And is the turbulence that's generated by calving icebergs, is that significant? Does it affect the pattern of fjord circulation that you might otherwise expect? Is it an important source of energy for fjords, or is it just something that's curious and fun? I think that's a very open question right now. And yeah, so with that, I'd be happy to take any questions you might have. Thank you.